Welcome, physics friends, to 15.2 part 2, and it's talking about resonance in air columns. I'm sure that you guys have all at some point in time taken like a soda bottle and you blow over it, or you maybe when you're a kid you have like a recorder here and you or even maybe I've got this guy right here. This is a it's like a slide whistle, big old. And you just vary the length of this thing. Now, what you maybe don't know is, or some of you can maybe even do this. I can sometimes do it, not always. That's the difference between what's called an open pipe resonator. So I can take my little recorder here, take the end off. I have an open pipe and a closed pipe resonator, and they work basically on the same principle, but they're different, and it's really kind of complex what's going on. So what I did is, this is considered like a soda bottle would be considered a closed pipe because one end is closed and one end is open. We consider this a closed pipe resonator. If both ends are open, like here on this one I was opening up this end, open pipe resonator. If I close the end, closed pipe resonator. And you can actually hear that's an octave jump between the two. Why does it do that? That's what we're going to answer today in 15.2 part 2. So what I did, I found a really interesting graphic that kind of shows what's going on inside of a. So what I've got here right now, this is a closed pipe, and I could make it an open pipe, open on both sides. So we'll start first of all with a closed pipe resonator. What's going on is this at the closed end over here. The closed end is a node. The air molecules that are vibrating inside there can't move because of the closed off end. So at the end you always have a node. And then this open end, the air is able to go in and out, vibrating in and out. This is an antinode. So right now this is the fundamental. When I play this right here, that's the fundamental, the lowest frequency that can be played. Now when you look at this and this displacement going on here, this graph right here, this is 1/4 of a wavelength. And that's important to understand, that this distance right here from here to here is 1/4 of a wavelength. Because if this was, if you've got a wave, so this is 1/4, 2/4, 3/4, 4/4. So this tube that I've got, my soda can or whatever, this tube right now is 1 meter in length. This tube, because I've got it set, the length of the tube is 1 meter. So that means that the wavelength, remember this, if this whole thing is 1/4 of a wave, the whole wave is going to be 4 meters. So that's where you see the wavelength of 4 meters. So you can actually predict the frequency if you use that equation, velocity equals wavelength times frequency. So if you have velocity equals wavelength times frequency, and the velocity is 343, your wavelength being 4, you could figure out the frequency by taking 343 divided by 4. And that gives you the frequency of 85.9. Fun fact, this is why when you're tuning your instrument, you have to retune it after your instrument warms up, because it warms the air inside there from thermodynamics, and then the speed of sound actually goes faster. So this actually gets larger, which means that your tuning is off, so you have to make sure that you adjust your tuning after your instrument warms up because of this. Now, So this is how we can predict frequencies from a closed tube. Now, there's more than just this is what happens here. Check this out. I can actually go one more higher. Like when I've got my soda bottle here, I can actually play more than one note on this if I blow a little bit harder. There is more than one frequency that can resonate inside these tubes. So here, it looks a little bit more complex, but what's still the same is on the closed end, I've got a node. On the open end, I've got an antinode. But remember, my tube remained a fixed length. It's the same length tube, but now this is no longer 1/4 of a wavelength. This is 3/4 of a wavelength. Do you see it? 1/4, 2/4, 3/4. So if I wanted to get my full wavelength, what does one wavelength equal to up here? It's a third more than that. 1, 2, 3, so it's 1.33, and that's where the wavelength of 1.33 comes from. And you can figure out the frequency from that velocity equals wavelength divided by frequency. And maybe you're going to start to see a pattern here. Remember, the fundamental was at 1/4 of a wavelength. What we've got right here, this is 3/4 of a wavelength. Let's look at the next one and see how many wavelengths this one is. 1/4, 2, 3, a full wavelength plus 1/4, 5/4. And it goes up and up following this same pattern. 1, 3, 5. Your guess would be the next one's going to be 7, and you'd be right. You go higher, one more. Erase my last line, and we're looking at 7/4. A full wavelength and 3/4, 7/4. So when we've got a closed tube resonates at 1/4, 3/4, 5/4, 7/4 of a wavelength, but every time it steps up by half a wavelength. Whoa. And again, my computer's being a little laggy here. Stepping up by 1/2 of a wavelength each time. Now let's go to an open tube and see the similarities and the differences between a closed tube and an open tube. Now, you'll notice that I'm pointing to this transverse wave right here. This is a transverse analog to really what's going on inside the tube. Really inside the tube, it's a longitudinal wave. The air is vibrating inside longitudinally, but sometimes to explain, there's the transverse equivalent here. So now I'm going to make both sides open. So I'll go back down to my open tube. Now, I've got an open tube resonator, and you'll notice similarities. It's similar because I have to have an antinode wherever it's open. If I've got an open end, there's an antinode. So what I've got here is I've got an antinode on both ends of this. So when I look at this wave, it's not a full wavelength. This is a half of a wavelength, or 2/4. This is 1/4 of the wave, 2/4 of the waves, which is half of a wavelength. So if I wanted to figure out what frequency would resonate here, I'd take my wavelength, which is 2 meters, My velocity equals the wavelength times the frequency. My velocity being 343 again. The wavelength being 2, the frequency 343 divided by 2 is 172 hertz. Now, I don't know if you were paying attention, but this is double what it was when this was, so 172, what was it when one side was open? 85.9, exactly half, because that in that case, I divided it by 4. This is why you get the octave jump. When you've got a closed tube, it's a lower frequency at the fundamental, right here. When I switch it to an open tube, exactly double the frequency. It's an octave jump. Now let's step up and see the other frequencies that resonate here and see if we can see a pattern like there was last time. So I'll go one higher. This is, what do we got here? 1/4, 2/4, 3/4, 4/4. So 1 full wavelength. Let's go to my next higher one. Maybe you can start to see the pattern here now. This one I've got 1 full wavelength and a half, or 6/4. Go one higher still. 8/4. So this is 2 full wavelengths resonating inside of this. Now just like, so it's different than an open tube in that we get even multiples. 2/4, 4/4, 6, 8. There's antinodes on both ends. So, but they're the same in that every single time they step up by half of a wavelength. Each time it's going up by 1/2 of a wavelength. 2/4 every single time. So this is what's going on inside of this is called cavity resonance. And here's an example problem. Your book, my notes, I put these in here. So here's, I couldn't have an animated thing like I've got up here, so I grabbed this from your book and I put this into your notes where you've got an open tube, so you've got half a wavelength, 2/4, 4/4, 6/4 of a wavelength going on. And then when you've got a closed tube, you've got 1/4, 3/4, 5/4. And here's an example. Here's the example problem. Let me switch over here. It says when a tuning fork with a frequency of 392 hertz is used with a closed pipe. So I've got a closed pipe here. And I've got my tuning fork, 392 hertz. The loudest sound is when the column is 21 centimeters. When the column is 21 centimeters. So here I've got, who knows what's going on inside of here? All I know is that I have to have an antinode on this side, and I've got a node on that side. So who knows what's going on inside this tube? But this whole thing is 21 centimeters long. Now it says, and the next is at 65.3. So I take this tube and I'm going to make it longer wish my computer wasn't so laggy right now. It'd be a lot easier to draw. Who knows what's going on? This distance is 65.3. The key to this is that remember that these differences between here were always half of a wavelength. That's the key. Half of a wavelength. What's going on is that I've got that same pattern, but then I've got an extra half of a wavelength on the end. I've got an extra half of a wavelength stuck on here. And that difference between 65.3 and 21, I subtract those two, and it's 44.3. So the difference in length, the difference in the lengths is 44.3. That's also half of a wavelength. And that's the key to all these resonant things, is that the difference between resonant points is always half of a wavelength. So that means that my full wavelength is going to be 88.6 centimeters, or 0.886. So I can figure out what's the speed of sound. So my speed of sound, it's the wavelength times the frequency. The wavelength being 0.886. And my frequency is 392. So when I multiply 0.886 by 392, I'm hoping it's around 343. 347. It must be a little warmer, or they're at a little bit higher pressure. Sorry about my computer being so laggy. 347 hertz. This is what's called cavity resonance. We can find the speed of sound. We'll find the speed of sound using this in class. And in the next chapter, we'll use cavity resonance to actually find the speed of light. Just knowing that the spacing is half of a wavelength. It's a really important thing to know, that the spacing between there is a half of a wavelength, and that the difference between an open tube, open on both sides, meaning that they start at 2/4. So 2/4, 4/4, 6/4, 8/4, and then when you go to a closed tube, it starts at 1/4. It does the odds: 1/4 of a wavelength, 3/4 of a wavelength, 5/4 of a wavelength, and so on.